In this first video, we're going to talk about growth models, and the two models we'll talk about will be linear growth and exponential growth. We're going to compare the difference between those two by looking at investing money in two different accounts. Each of those will be earning 20% annual interest. That'll be easy to see the difference between compound and simple interest growth in something that large. We'll call one account S for simple, that'll be the simple interest account, and the other account we'll call C for compound, which will be the compound interest account. So let's compare what happens with the two account values over 10 years if you start with $1,000 in each. Account S will be earning 20% simple annual interest versus account C, which will earn 20% interest that is compounded annually. So the first thing we'll do is we'll take a look at those formulas for simple interest and for compound interest. Now, for simple interest, you'll take the principal P and you'll add this PRT, if you recall, is the interest that you'd earn. So if you invest a certain principal for a certain amount of time at a given rate, that will give you your principal plus your interest will give you your new account balance. So the general formula for our situation, the principal we're investing is $1,000, and we'll add on to that, this is 20%, 0.2, times T. Now if you invest for 1 year, you get 20% of $1,000 for 1 year. If you invest for 2 years, you get 20% of $1,000 for 2 years, and so on. And so you have these formulas where T is getting bigger for all 10 years. And so we'll take a look at our calculator. We can put this in our calculator to do this a little more quickly. You may have to do this one step at a time if you don't use a calculator that you can enter a formula in. So we're going to enter the formula in as 1,000 plus 1,000 times the interest rate, which is 0.2, and times, I'm going to put X there because that number is going to vary. So that's our variable X. They use X in the calculator. I'm using T here. It doesn't matter what the variable is. Now on this calculator, you can go to the table, and you go second table set. We're going to start at 1 year, and we're going to go up by 1 year at a time. And we'll tell that to automatically calculate that. So now we're going and look at the table, second table. And you can see after 1 year, the account balance is $1,200, then it goes to $1,400, then $1,600, and so on. So this would be $1,200 after a year, which means you start at $1,000. 20% of $1,000 is, of course, $200 for 1 year. So you made $200 in interest, right? So I'll just put a little comment here, $200 in interest. The next year, you'll see it's $1,400. And so, how much interest have we made now? Well, we made a total of $400 interest, but that's an additional $200, right, in interest every year. And then if you noticed, it goes up by 200 every year because all you're doing is multiplying 20% of 1,000 by, instead of 3, it's 4 and 5 and 6 and 7. So you're getting one more year of interest, and you're making $200 in interest every single year. So you might as well, you don't really need a calculator for this. You can just add the 200. Year after year after year, you're getting $200 more in interest. 2,800, and then finally we'll have $3,000 at the end. So notice it went up by, I'll just make a little notice here, it went up $200 there, and then $200 there, and then $200 there. And that's how simple interest works. You have an amount of money, you make a certain amount of interest on that money, and then they kind of expect that that $200 either sits on the side and doesn't get touched, or you could take it out and use it or something, but the only thing you're making interest on is the $1,000 investment. So that's a linear growth. It increases by a constant amount each time. The difference between all of these is 200. So that has a constant difference. Okay. That's the basic idea of linear growth. Now, exponential growth is a little different. With compound interest, when you make a little bit of interest, then that money goes back into the account, and the account value is a little bigger. And so you're making interest on a new amount every year. And so if we put this formula into the calculator, by the way, that comes from this, you may remember the compound interest formula, the principal times 1 plus the rate over K is the number of times you compound in a year with an annual rate. And in this case, the year is 1. So R is 0.2 and K is 1. We're compounding once a year in this particular situation. So we get 1 times T, which is always just going to be T. And 0.2 over 1 would be 1 plus 0.2. So that formula is going to look a little different. I'm going to put that in another one. That's going to be 1,000 times 1 plus 0.2, which is just 1.2, to the, now there's, instead of T, I'll use X, because that's what the calculator uses, to the X power. Now we can go to the table. It's already set up for us by going year by year. And this has saved us quite a bit of work, because now, rather than going up by $200 every time, which didn't require the table, now we see that after the first year we earned $200 in interest. So this was $1,200. So it did go up by $200, right? But what happened the next year? It looks like it went up by how much? That number is, if you can't see that, $1,440. So that went up by $240 the second year. The third year is $1,728. Because after the first year, we were making 20% on $1,200, not just 20% on $1,000 like we were in the previous linear model. So this is an increase of what? 1728 minus 1440 is what? $288. If you want to take 17, you can always find the difference by you subtract the number from the previous number from the given number there. So that's going to be 8. That'll be 8 when you borrow, and you get 2. So it's $288 is the increase. Now you could go to your calculator, and in each one of those you could put these into your calculator to calculate it. The next one is 1,000 times 1.2 to the 4th power. I don't really need parentheses around the 1.2, but that's 2,073.6. Now if we go back to the table, we'll see that that was giving us 2,073.6, but I only had to put in the formula once because it generates all the answers for me. So I'm just going to write these out. This is 2,073.6. And that is going to be an increase of 2,073.6 minus 1,728. So that's going to be 0.6. 13 minus 8 is 5. This will be a 6. 6 minus 2 is 4. 20 minus 17 is 3. That's an increase of 345.6. So notice, not only it's going up quite a bit. Here, the first jump was $200, then it went up by 40 more, 240, then it went up by 48 more, and that's almost a 60, it's a little over a 50, almost a $60 increase in how much the account is increasing. So it's increasing at an increasing rate even. This is increasing at a constant rate. So if we went ahead and finished these, let's go ahead and I'll write all those numbers out. 2488.3, 2986, 3583.2, no, that's 20 cents, 4299.8, and these are rounding off to the nearest tenth. It's actually, some of these you have more numbers. This is actually 32. This is actually 18, not 0.2. This is 18 cents actually. That is 80, really 82 cents approximately. Then we get 51, 59, 78. And finally, after 10 years, we're at $6,191.74. And let's look at how much that has jumped by now. At the end, we've got 6191.74, minus 5159.78. Go ahead and subtract those. I'll put that in my calculator. 6191.74 minus the 5159.78, and that gives me $1,031.96. So the last year there, out of the 10 years, it increased by over $1,000. Obviously, you can see that, 51.59 to 61.91. So the increase was increasing, and that is what is kind of indicative of exponential growth. So let's take a look at the graph of both of those, because that's kind of what is another way to hopefully emphasize the difference between the two. So if I graph these tables, basically, for 1 year it's 1,200, 2 years it's 1,400, 3 years it's 1,600. Let's take a look at what that will look like on the graph. So at year 0, they are both accounts are at $1,000. That's where they both start. But in the first account, this went up by only $200. Well, this is 1,000, so this would be a $500 jump. So 200 would be right about here. And then rather than putting every point, I guess the next 1,400 would be right about here. 1,600 would be right about here. Notice it's going up by a constant amount. So let's jump all the way to, at year 5, it's at $2,000. And then by the time we get to year 10, it's up to $3,000. So all these would be kind of every $200 every year. So that's what that would look like. Very linear, right? It's a straight line. That's linear growth. Now, we're going to take a look at the exponential one. And that's why I made this grid, so it's going by thousands or really by 500s. And now if I wanted to jump, I made a kind of a jump here to 1,000 because I didn't really need anything below 1,000. That wasn't actually necessary. But now if I start plotting these values, the next year, after 1 year, it was also at $1,200. This one was too. But then it went up, instead of 1,400, it went up to 1,440, just a titch higher after year 2. This one was 1,400, and this one was 1,440. Year 3, it went to 1,728. Now, that's 1,500, and that's 2,000. So 1,750 would be right in the middle. So that's 1,728 is right about there. And then 2,073 at year 4 is 2,073.6. So that's going to be a little over 2,000. And then year 5, we've got 2,488.32, really close to 2,500, just under 2,500. So that's right there. So you can see it's outpacing the linear a little bit. It's starting to curve up. The next year's 2986. That's just a smidge below 3,000. So here at year 6, we're almost to 3,000, where it took 10 years to get to 3,000 here. But now you really see some booming growth. This jumps up to 3,583, over 3,500 in year 7. So that puts us up to right about here. And then 4,299, so about 4,300 at year 8. We're getting to be bigger jumps. 4,000, this is 4,500, so 43 is right about there. Then 51, about 60. That's going to put us up to, here's 5,160, probably right in there somewhere. And then finally we exceed 6,000 at year 10. So that's the biggest jump, almost 6,200, pretty high up there. And so you can see this exponential growth looks like this. It increases, and both of them are increasing, but this one is increasing at an increasing rate. You may remember that this is called concave up from your study of either exponentials or quadratics as well on parabolas. Okay, that's the end of this introductory lesson on exponential growth versus linear growth.